Our next speaker is Siva Theja Maguluri from Projectable.
Thanks, Ajay. Thanks for inviting me. Good afternoon, everyone. Thanks for stopping by my talk. So I'm going to talk about reinforcement learning. This is joint work with my former student, Ziva, who is currently postdoc at Caltech. And Ziva is not here right now. I don't know if he's watching online, but he's going to be here starting tomorrow. He'll be at the workshop next week. And Ziva and I are going to conduct a joint tutorial on Monday at the workshop. The tutorial relates to some of what I'm going to talk about today, and I'll point out as we go along. So I guess I don't need to really introduce reinforcement learning. There's so many success stories. I think every year there'll be a new Nature paper about success of reinforcement learning in one new application, starting from AlphaGo to protein folding, navigation, manipulating robotic arm, manipulating plasma in a collider, and so on. And at the heart of it, a reinforcement learning problem is modeled by what is called as an MDP, Markov decision process. So I'm trying to give a very quick overview, a 3-minute overview of introduction of reinforcement learning before I jump into my results. So there's typically an agent, and there's an environment which represents the state around the agent. And the agent interacts with this environment by taking an action at each time. And the environment responds in 2 ways. One is that it moves to a new state and it gives a reward. And the goal of the agent is to maximize long-term rewards. And this is the classical Markov decision process model, which is used extensively in various engineering problems. The main difference in reinforcement learning is that the transition probabilities, the probabilities of next state and reward, given the current state and action, are unknown. So you have to learn them as you go along, or more precisely, you actually don't care about the transition probabilities as such. You want to learn the policy that maximizes the long-term reward. And by policy, what I mean is that a mapping, every time you go to a state, you take a particular action, or you sample actions from a particular distribution, and that's given by the policy. So typically, to do anything with reinforcement learning, we need to work with value function. And there's something called the V function, which is used in classic MDP theory, which is simply the long-term total reward. And I'm working in the infinite horizon discounted cost setting. So if I sum all the rewards, it'll go to infinity. So I discount them with the inflation factor gamma. And so if I start in state S and follow a given policy pi, I take actions at every time from this policy. When I look at the long-term reward, that's denoted by V pi S, and I can tabulate all of these in a vector for different starting states, and that's my value function. There's something called the Q function, which is used in reinforcement learning and not classical MDPs, and I'll explain why in the next slide. It's defined analogously, except that my starting state is S, my starting action is A. At time 0, I don't follow the policy, I just take my action A, and after that I follow the policy. And this is defined as a function of S and A, so this is a bigger vector. The size of this vector is S dimensional, the size of this vector is S times A. I'm working with finite state and action spaces. So even though these are functions, for me, they're just vectors because S can only take finite values and A can take finite values. And the goal is to find the policy that maximizes this V pi. This is a vector. What do I mean by maximizing the vector? It turns out there is a policy that maximizes all the components simultaneously, and that's what I'm interested in. Typically, to do this, sometimes people think of a smaller goal, which is given a policy pi, I want to find the corresponding value function, either V function or the Q function, depending on the setting. And that's usually called the policy evaluation problem. Now, so for the policy evaluation problem, I want to find V pi for a given pi. And turns out V pi solves this equation. You don't have to parse this equation. The only thing I want you to understand about this equation is that V pi shows up on the left-hand side and the right-hand side. And there's some complicated expression here, which involves the expectation. So the whole thing is linear. And this expectation involves the transition probabilities I don't know, which means I have to solve this fixed point equation when I don't know this operator. And similarly, if I want to solve the control problem, then one way of doing it is to find the value function corresponding to the optimal policy. So here I'm illustrating it with V. Here I'm using Q. Q star is the value function of the optimal policy, and it satisfies a Bellman equation that looks like this, which is very similar, except that there's a max here, and because of that, it becomes a nonlinear equation. And this is again yet another fixed point equation. And the reason I care about this optimal value function is because if I can find this Q star, then my goal is to find the optimal policy, remember? Then I can simply take the Q star and do the argmax For each state, I do argmax over actions, and that will give me the optimal policy. So finding Q star is as good as finding the optimal policy. Okay, good. So reinforcement learning is essentially solving either for this or sometimes the policy evaluation problem when you don't know the underlying operator. And so there are two, if we again step back from reinforcement learning and go to MDPs, there are two approaches that people use, value iteration and policy iteration. But before I talk about that, any questions with the setup so far? Okay, good. So I'll not talk about value iteration too much, or I might in a bit, but I'll focus on policy iteration in this talk. In policy iteration, it's a two-step process. It's an iterative process where there are two steps in each iteration. The first step is to do policy evaluation. So you start with the initial policy pi, and at every time, you keep iterating through a sequence of policies. At every time when you have a policy, you evaluate it, which means you find the corresponding value function, either V function or Q function, depending on the context. In RL, we'll work with Q function. And then once you have the Q function or the V function of the corresponding policy, you do policy improvement by going to a next policy, which is better. And to do this, if you had V function, to find this better policy would involve knowledge of the underlying model, which we don't have. That's the reason in RL we work with the Q function, so that if I just do argmax among the actions, then I would get the next policy. Now, how do I do policy evaluation? Policy evaluation, remember, just reduces to solving a fixed point equation for the value function. And that can be done using something called value iteration, where you just keep applying the operator again and again till you converge. So this is the high-level scheme. So there are methods in RL focused on value iteration. I'll not talk about them today. I'll talk about them on Monday at the workshop. But today I want to focus on policy iteration. And if I want to adopt this approach in reinforcement learning, what we get are called actor-critic methods. So instead of policy iteration, we call it actor-critic. The idea is that I have to iterate through these policies without knowing the model. So I have to sample from the environment. And the policy evaluation is done by the critic. And now the critic uses something called TD learning or its variance to evaluate the policy instead of value iteration, because we don't know the underlying operator. And instead of policy, the policy improvement is done by actor. And the problem, there is one challenge here. So if you want TD learning to work, it will work only if you explore all the state action spaces, states and actions. So even if we forget about all the details, the idea is that if you want to find the optimal policy, you should at least check out all the states and actions. Otherwise, it doesn't make sense that you can find the optimal policy. And for that to happen, you want your policies to be exploratory enough. You don't want your policies to be deterministic. You want them to be randomized policies at every time. So if you do argmax, you will end up with a deterministic policy like in one step, and that's too bad. So people do variance of this argmax, and that leads to various algorithms called policy gradient, natural policy gradient, and so on. And let's look at this in more detail. So what I'm going to do in the rest of the talk is I'll spend the next several minutes talking about the actor, and we'll present our results on the actor. After that, I'll talk about the critic, then I'll put everything together and present the results for actor critic. This is what is coming up. Questions? Good. So I said that in MDPs for policy improvement, one simply does argmax, and I don't want a deterministic policy. I want a stochastic policy. So a natural thing would be to approximate it by a softmax, and we have already encountered softmax this morning. Softmax, I'm not writing it exactly, I'm just saying proportional to, and this parameter beta can be thought of as a tunable parameter, which I'm going to tune eventually. And if beta is very, very large, then this softmax essentially becomes argmax. And this pi will become ones and zeros. So in fact, this can be thought of as some kind of approximate policy iteration. And the results in our paper and the results I'm going to show are also applicable to this setting. But in this talk, I don't want to focus on this. Instead, I want to focus on this. So what I do is I take the current policy. I use the current policy also while doing the argmax. So somehow I multiply the current policy with this exponentiation. This is also yet another approximation to do policy improvement. And this algorithm is called the natural policy gradient. So I'm introducing it as some kind of weird approximation of policy improvement, but there are many, many interpretations of this. One is what I just talked about. The second interpretation is it can be thought of as mirror descent, generalized to reinforcement learning. Mirror descent and optimization, generalized to reinforcement learning. And mirror descent, when you have a simplex constraint, can be written in terms of multiplicative weight update form. This is the weight update form. And we talked about preconditioning this morning. And this can also be interpreted as simply doing gradient descent with a feature information preconditioning. And this can also be thought of as regularized MDPs. There are many, many, many interpretations of this. I think initially when it was introduced by Shyam Kakade in 20 years ago, he actually thought of it as preconditioning. Okay, so the result I want to state in this context is that this is the first result that I'm stating, is that under appropriate choice of step size, I'll come back to this. So I'm only thinking of the actor for the time being. I'm not worrying about the critic, because to actually implement this, I need to evaluate Q pi k. For the next few minutes, let's pretend that a genie gives me this Q pi k exactly, but eventually I have to estimate it. Then if I run this update, I have the following convergence, Q star. So here, I actually don't even care about Q, I care about the policy. The policy after capital K iterations is my pi k. And I'm saying that's good. Good in what sense? If I look at its value function and compare it to the optimal value function, then the difference of that is going to decay geometrically fast. The two terms, sorry, this is wrong. This should be Q pi 0. This is Q pi 0. This is a typo. So this decays geometrically fast. Gamma is my discount factor, which is less than 1. The second term also decays geometrically fast. Now, what is my beta k? It doesn't depend on any unknown in the system. The only thing it uses is the current policy. The policy, this is like a matrix. For every state and action, you have a number. For every state, so you have to minimize over one. For every state, find the action that minimizes the current value function. That is this guy, and then look at the small minimize this over all the states. But whatever this is just a function of the current policy. And the main thing I want to highlight here is that the step size is actually increasing. Gamma power k is decreasing. It's in denominator, so it's increasing. So even though you can think of it as an optimization algorithm like mirror descent and so on, this is very counterintuitive. In optimization, you never increase step sizes. You either keep them constant or you decrease them. And
it's a weight, not a step size, right?
Exactly. So if you correct. That's the reason I introduced it this way. Once you look at it this way, it's very clear that beta should increase so that my approximation in the maximization is becoming better and better. But if you take the mirror descent viewpoint, the beta is going to be the step size, and there it's a puzzle as to why you would increase instead of decrease. Good. And very quick overview of related work. Natural policy gradient, like I said, was introduced by Kakade 20 years ago, and 3 years ago, Agarwal et al. Essentially presented the first proof of convergence to the global optimum, and they showed a rate of 1 over k, and they take the mirror descent viewpoint and work with KL divergence as a Lyapunov function. And one of the surprising result, this is a breakthrough paper in the space, and the reason being that before them it was not clear if this policy improvement methods even converge to the global optimum, and they showed that it converges. They do converge to the global optimum, even though the corresponding objective here turns out to be non-convex, and they got a rate of 1 over k. And there is some follow-up work where people showed, I mean, these papers are actually 2 years old. These are the accepted journal versions, but they first came out 2 years ago. These two papers show geometric convergence, but once they regularize the objective. By adding a regularizer, you speed up the rate of convergence from 1 over k to geometric. Geometric is also called linear convergence in optimization literature. And they still exploit the mirror descent viewpoint. What the main message I'm trying to convey in this part of the talk is that you don't need regularization. Even without regularization, even though your objective is non-convex, you will have geometric convergence. And the reason is that convexity and optimization viewpoint is not the right way of thinking about it. This problem is not a random convex optimization, random non-convex optimization problem. It's actually there's this nice Bellman operator sitting at the heart of this problem, which has contractive and other nice properties. And because of that, we get geometric convergence. So our proof essentially goes back to the MDP literature on approximate policy iteration, and we exploit contraction and monotonicity properties of Bellman operator as opposed to worrying about convexity. I'm focusing on one particular algorithm, natural policy gradient. There are many other algorithms that go by policy gradient that go under policy gradient umbrella, and there's also a lot of prior work on approximate policy iteration, especially in the OR community. So I'm not at all being exhaustive. I'm not even trying. Any questions so far? Yes.
In practice, does it work better with the regularization or without it?
So we did do some simulations. We saw that even without regularization, it's doing fine. It's converging. We saw the geometric convergence, but we haven't actually compared it with the case of regularization.
If I take the step size to infinity, like cover positive iteration.
Yes, you do.
And do I still get the linear convergence?
Yes, policy iteration actually has not just linear convergence, it's finite convergence. After there's a finite number of steps, after that it finds the optimal.
In SA number of steps it will converge.
Yes. Yes.
So why I should not take infinite steps?
Because if you do that, your policy will become deterministic. And I haven't talked about the critic. Remember, I said that let's pretend QPi is given.
Oh, yeah.
That breaks down later. So at this point, compared to policy iteration, which converges in finite step, this looks like a step back, but everything falls in place when we go to active critic, the final theorem that it is. More questions? Oh, cool. So in reinforcement learning, everything I talked about so far is called tabular setting because I'm working with the full state space, action space in SA dimensional space. And that's a very high dimensional space. In reality, people like to approximate it by a lower dimensional space. So essentially what you do is my Q function is a SA dimensional vector. SA is huge. I come up with D feature vectors. My phi's are feature vectors. Each one is a SA dimensional vector. I have D of them. And I basically live in this lower dimensional subspace. I approximate my Q function by a linear combination of these D vectors. And I want to find the best possible approximation. And my policy is a function of state and action as well. For each state, for each action, what probability should I take that action with? So that also is a SA dimensional object. And I want to approximate that as well. And what I'm doing here is that I'm using the same feature vectors to represent both Q function, to approximate both Q function and the policy. And this is the right linear function approximation in this setting. And notice that let's first fix a policy pi. The corresponding Q function, Q pi, may not lie in this subspace. It's living somewhere outside. So I can't even find Q pi if I want to work only in this subspace. And then what I would do is, so even though at this point I haven't even still gotten to the critic sampling from data, but still, because I only work with lower dimensional objects, even the Gini critic cannot give me a SA dimensional vector. So I have to approximate this Q pi by something. And what we use is projectable equation. We did not introduce this. This is well known from the late 90s, but I believe this was not used in the actor critic setting before our work. So the idea is that suppose you have the corresponding Bellman equation. Earlier I had Q pi equal to H pi of Q pi. Now I introduce the projection step, which means the fixed point I'm trying to find is I want to find a Q tilde in the subspace such that if I apply H pi, it goes outside the space. It can possibly go outside the space. I can't help it. But if I project it back, then I come back to the space. So this is some kind of approximation of the real Q pi. So now let's say that this is what I do. So instead of working with Q pi k, exact Q pi k, I work with these lower dimensional approximations for both pi k and Q pi k. If I were to do that, this update equation becomes very simple. It's just this equation. Now pi is represented by this phi times theta. So instead of working with pi k plus 1, I'll work with theta k plus 1 because theta is a d-dimensional vector. So theta k plus 1 is simply going to be theta k plus beta k times w by k. And this w pi k is the solution of the projected Bellman equation. So now what is going to happen? So because I'm doing these projections at every step, I'm actually going to incur some errors. There's nothing I can do about it. And this theorem, the first two terms are same as before. So now again, I'm looking at the policy at the end of k iterations. I'm looking at the corresponding error. And this is geometrically converging, but it's not converging to 0. The error goes to, this terms go to 0, but now I have introduced a constant error. And what is E approx? It's basically whenever I project from this higher dimensional space to the lower dimensional space, the error I'm introducing, the maximum value of that is this E approx. This is the approximation error due to function approximation. In some sense, it's inevitable to have this even in the policy evaluation problem. But now when you put it all together within the NPG framework, what we are saying is that we end up with a blow-up factor of this gamma over 1 minus gamma whole square. And turns out that for this approximate policy iteration class of algorithms, this blow-up factor is inevitable in the sense that there's an example presented by Bertsikas and Tsitsikalis in their book, which shows that this is inevitable for any API algorithm. Any questions on this? Yes.
You have the approximation error for the Q function. Does the approximation for the policy play a role?
Not quite. It doesn't come up directly, but I'm using the same feature vectors for both policy and Q. So in some sense, that is taken care of. That's one way of thinking about it. Another way of thinking about it is that this approximation can be thought of as the maximum possible approximation in the policy evaluation. Even that statement is not quite correct. Because Tsitsikalis and Van Roy introduced the projectable equation, they show that the approximation error they get is this times 1 over 1 minus gamma. And what I am, because I'm taking that machinery and putting it within the actor critic framework, I'm getting another 1 over 1 minus gamma factor.
What if your policy does not share the same feature representation as the Q function?
Why should it share the same feature vectors? Yeah, actually, that's a good question. This is again something that goes back to Shyam Kakade. So writing a clean update, if you work with different feature vectors in both spaces, is going to be messy. The way it's presented in the original paper is that you should have a compatible function approximation representation. The representation you use here and the one you use here should be somehow related. If you are working with policy gradient, that relation is not identity relation, but in our natural policy gradient, the relation is that they're the same feature vectors. That's another nice thing about natural policy gradient. But if you don't do that, I think everything breaks down pretty much. Even the algorithm will not start making sense. Sure. That's another way of saying, I mean, that satisfies this assumption. Good. That's a good observation. More questions? Okay, cool. So far I talked about actor alone. A genie was giving us the value functions in the tabular and the function approximation setting. Now I want to attack the question of how do you find this value function. So I'll directly work in the function approximation, linear function approximation setting, and recall that I want to solve this projected Bellman equation. And since I'm living in the lower dimensional space, my Q pi can be approximated by phi times W pi. And due to linearity, so everything here, the Bellman policy evaluation operator is linear, and the projection also turns out to be linear. So you can show that this equation is essentially a linear equation of this form. I'm not showing what this A and B are. A and B depend on the policy, on the Bellman operator, on the feature vectors, everything. But essentially, it's a linear equation of this form. And the only problem is that since they depend on the underlying model, I don't know this A and B. If I knew A and B, I could just invert it, yes.
And just to, we agree that A it is not necessarily invertible or full rank, especially because of the projection, right?
Turns out that it is full rank actually, because I mean, you go from SA dimensions to D dimension. In fact, it can be shown that A is Hurwitz. All its eigenvalues are negative. D is less than SA. So it will be invertible. So if you want, you can invert it. But the only reason I can't invert it is because I don't know A.
Invertible when you represent the projection.
Well, in the space.
Feature vectors are linearly independent. I mean, I'm not solving a SA dimensional thing. My W is a D-dimensional object. Originally, I was in SA dimensions, which is big. From million dimensions, I project to D dimensions, 10 dimensions.
Okay.
So it's not surprising that it's.
Okay.
So when we have noisy access to A and B, which means at every time I can sample a copy of A and a copy of B, but I'm getting noisy samples. Moreover, turns out that what we have were Markovian samples. So it turns out that the right way of solving this is using stochastic approximation. So essentially, I'm doing wk plus 1 equal to wk plus my step size times, I'm trying to solve aw minus b equal to 0. That's exactly what I wrote here, plus noise. So if there is no noise and if step size is, okay, never mind. So this is called stochastic approximation. And if you want to understand more about stochastic approximation, you should check out my tutorial on Monday, because Sanjay said I have only 5 minutes, so I'll just keep going. So I'm not going to show what A and B are, but if I substitute the right values of A and B, and after massaging it a little bit, what I get is the famous TD, temporal difference learning algorithm. The whole motivation here is just to get to temporal difference. All it says is wk plus 1 equal to wk plus step size times my feature vector. All my features, I have my D feature vectors, right? Evaluate them at this component. So I have a policy at each time. I take an action with respect to that policy. I look at my current state and my action, that gives me a tuple. I evaluate the feature vector at that tuple and then multiply by this delta, which is called the temporal difference. And this is simply my current reward plus gamma times, ignore this gap for the time being, plus something that again depends on the phi at the samples and this W. Now I'm interested in not only doing this policy evaluation, I want to do it in an off policy setting, which means I want to evaluate policy pi, and in each iteration of the actor critic, my goalpost is changing. First, I want to evaluate pi 1, then pi 2, then pi 3, and so on. And but I want to keep sampling with a fixed policy pi b, because maybe my data was collected a long time ago using a given policy. Maybe think of clinical trials as an example. So then it turns out the right thing is to change this algorithm by simply presenting an important sampling factor here, which is just the ratio of the policies. And turns out if I do this, it's not going to work. There's a counterexample from, this is a very old counterexample, but I'm citing the book. So what they say is that if you have function approximation and you are working in off policy, then there is convergence, and that phenomena is called deadly triad. And what we do is, and the reason for this is because now when I'm doing off policy sampling, the projection I'm doing is with respect to my sampling policy, and I'm trying to evaluate a target policy, and these two don't commute. These two are not consistent, and the overall thing is not a contraction. So what we say is that you should use n-step TD instead of one-step TD, and then all that means is that you take the temporal differences over the last n steps and add them up with the corresponding importance sampling ratios and discount factors, and this works. So putting everything together, I think the quick takeaway is that if you use n-step TD with importance sampling, that overcomes deadly triad in the off-policy setting, and that can find the solution of the projected Bellman equation, and the rate of convergence is this. W pi is the solution of the projected Bellman equation. If I run this inner loop, if I run the critic for t iterations, then the rate of convergence, if I use a constant step size, it's going to be, the first term is geometric, so that's not problematic, but the second term is a constant that depends on my step size. If I make my step size small, then this error is going to be small. So now, picking the right step size, I can show a rate of convergence of 1 over square root of t, or sample complexity of epsilon power 2. So pretty much my last slide. What I'm going to do now is put everything together in the actor critic framework. So I have my critic. I want to do actor critic with a linear function approximation, natural actor critic to be more precise. And I'm doing off policy sampling and n-step TD with importance samplings, and I run it for t iterations and within each step of the actor. And then for the actor, I'm doing natural policy gradient with linear function approximation, and I'm running it for k actor steps. So totally, I'm using tk samples. Then the theorem essentially puts everything together. So the first two terms come from natural policy gradient in the tabular setting. This was the function approximation, and this is the critic error. And everything together gives an overall sample complexity of epsilon power minus 2, which turns out to be the optimal rate. And I'll stop here.
Thanks. Question, we can take it now, or we can go to the break and chat. Okay. Then we just take a break for 10 minutes and continue.